I'll divide the presentation in 4 parts. A little bit of what we do at IRENA and what we do in the power sector in particular. Then I'll go directly into the topic of today's presentation, which is about electric vehicles and how we model those in PLEXOS and a couple of application insights from this, and then some general conclusion and future work. So for those of you that are not familiar, the International Renewable Energy Agency is an intergovernmental organization, which means we work with governments around the world. We have 160 member countries, pretty global memberships, and we look at everything renewable. So we work on all the renewable energy resources, from very high-level policy advice to governments all the way down to project development and anything in between, except we don't go down to the hardware level, so we stop at supporting project development. And in particular, we have different pillars in our work program. One of them is to be a center of excellence for the energy transformation, which is the key, let's say, connecting theme for the energy sector at the moment. So we look at everything that is between now and 2050, especially at the moment, and how to get there at least cost with the best strategies. And transformation pathways, especially in the power sector, is where the stream of work I'm talking about today is sitting. Our work on the power sector is built around a variety of pillars. One of them, of course, starting from the top, is supporting countries in designing their markets. There's been quite a lot of work, of course, especially if we look at, let's say, OECD economies and market design in the past, but there is plenty more work to be done in the future in the rest of the world. There's still a lot of vertically integrated utilities that might stay or might not stay, but definitely there is something that needs to be done on the regulatory framework if we want to see the speed of deployment that we need, and the enabling technologies as well. We do specific regulatory advice with countries, and we have a new stream of work that has been picking up speed, which is the innovation. So we work very closely in my team with the innovation team. So they look at the technologies and the business models that can get us to where we need to get in 2050, and we look at doing numbers for this. We have the usual division of modeling, let's say, pillars between long-term, short-term, and more reliability type of work. So we do a lot of work on energy planning. We have a large clean energy ministerial campaign running at the moment. We have regional workshops. We have in-depth country engagement with development of master plans. We do the PLEXOS type of work, especially around the ST in my team, where we look at flexibility as the main running theme, and we look at a few of the enabling technologies in more details. We are coming up with a large report on storage valuation, which speaks to the regulatory framework for storage, as well as technology and modeling of this. And we do a few analytical briefs where we try to take something, let's say, quite technical and bring it down to 20 pages for policymakers, trying to bring a little bit of clarity along some of the hot topics that are debated in the policy domain. And then finally, we do technical network studies. So we use software such as Power Factory and PSSC to do assessment of stability and other, let's say, reliability elements in especially isolated power systems. This is a stream of work that started in islands. At the moment, we are going a little bit larger scale, but still, let's say, few gigawatt is the largest. Typically, this is binding at the moment for very small power systems, and that's where we focus to date. And finally, we're trying to bring it all together based on the experience of some of the front-runner countries and building a knowledge framework, which means all that is not quantitative, all the experiences of member countries in finding solutions to specific challenges, how this has been developed, what are the approaches, methodologies, and especially what are the key solutions in all the domains from market to technologies that have been deployed to support high shares of renewables into the power system, with a strong focus, of course, on flexibility and enabling technologies for solar and wind integrations. So 2018 has been a busy year on the world of flexibility, not only for us, but definitely is a strong theme that seems to encompass most of what people are talking about when it's about integration of solar and wind. So we released one of our flagship reports on flexibility. We try to give it a definition. There's many definitions out there. We gave our own, and we try to look at the approach of all of a sector transformation. Just to give a bit of context, I don't have the usual IRENA slide on where we are heading, but I think it would be good to put a few numbers, at least what I have off my head at the moment on this. So we're looking at a 2030 system with significant more electricity in final energy consumption, and a lot of that being renewables, and means double speed of change. If we're looking at 2050 Paris compliance scenarios, we are looking at 86% renewables in power. That is about 2/3 of renewables in final energy consumption, which is quite far from where we are today, which is about 20. If we are looking at electrification, today we're at 20%. We are heading to 50%. So it means we're going from about 25% renewables in power with a final energy consumption which is only 20% electricity to 86% renewables in power with 50% of final energy consumption being electricity. So that there is quite a bit of need of changing the speed of what we're doing. And so to do that, we are shifting a bit the narrative on flexibility from flexibility in supply to flexibility everywhere in the system. So if 50% of final energy consumption is electricity, then we need much more of flexibility also here. So we're talking in many different fora about hydrogen. I would say it's the topic where we have the least economic case yet and the most interest, which is quite interesting because we need to match the expectations at one point. If everybody gets excited about it and then deployment is lagging behind, it's a challenge. We've seen this 15 years ago for those of you that were already in this sector. It's happening again with a much better framework at the moment. Power to heat, we don't talk about it much, but in economies where heating is the largest part of energy consumption, that is significant. And today's presentation will focus on electric vehicles. To give a bit of context, in this 2050 world that we're describing, electric vehicles will be 1.2 billion. So if we want to get there, we need these batteries on wheels, and we need them much faster than we have today. To go back to the innovation work stream, our colleagues released a few weeks ago an innovation outlook on smart charging of electric vehicles. It benefited from some of the insights that we developed in the work that I will talk about from the next slide, done in PLEXOS. And they also try to generalize some of these PLEXOS simulations to get some advice on strategies on how to best use the existing or expected electric vehicles in the system to facilitate solar and wind integration. So there are some fairly detailed pieces of analysis done about mobility as a service, about the different ways of charging, different ways of incentivizing charging vehicles in a certain way to make it system friendly, and so on and so forth. And also in this innovation outlook, there is some PLEXOS work behind. Going to the detailed piece of work, this started as a roadmap for an island country in the Pacific, Barbados, in the Caribbean, Barbados. And in this case, they had already a few electric vehicles being deployed in 2015 when we started the work. The work has been completed in 2016. We're doing an update now. It's currently with the government. The idea there is that they started quite quickly with PV and with electric vehicles, and there's very strong synergies between the two. And the new government now pushed beyond what we recommended, so they had an NDC of about 75% renewables, and the new government wants to go 100% renewables. And so in this context, being a very small isolated power system, they have a strong case for using the electric vehicles that are coming to the road to facilitate integration of solar and wind, especially wind is not there yet, solar is there, so there is a case for solar integration from electric vehicles that is quite strong. Easiest approach, looking at the three standard behaviors for charging electric vehicles. The first one is the system adequacy challenge one that we like to call, which is somehow the standard behavior. You come home, you plug your vehicle, charging at rated power, you don't have enough fixed capacity to meet that. The same amount of vehicles charge a bit more smartly, so giving control to the utility or putting a timer or doing batch charging, much more system friendly, doesn't increase system peaks, so no adequacy issue there. It's just going to increase the prices during the night. That's fine at low renewables penetration, but if you're going beyond that, you need something else, especially with large amount of solar coming into the system. Let's say the third approach that we suggest is the, let's say, public space charging, which tries to match solar generation with charging of EVs, and that's expected to work quite well, and you will see it actually does. So one additional piece here, trying to see how this fits into other streams of work. This initial work on electric vehicles has been also rolled out in the so-called remap analysis, our renewable energy roadmap for 2030 for Europe. So this publication here has been done in collaboration with the University College Cork, where we rolled out, in addition to the energy system analysis that we have for 2030, also a power system analysis in PLEXOS, and at one point we also added electric vehicles as one of the enablers, because we see quite a lot of electric vehicles coming into Europe by 2030. What is important maybe for the panel discussion we're going to have later is that this document is being quite influential in Europe to raise the level of ambition of the European Commission to get to 32% renewable in 2030. That means 50% in power, which is quite a bit. And in general, I think what is important is all this type of very technical analysis at one point has to trickle back to policy, and this is one of the good examples of how that has been achieved in the last couple of years. Getting to the equations here, a little bit more into the details of the modeling. So how did we model vehicles providing vehicle-to-grid services? So going from a smarter charging approach to using these batteries on wheels to integrate more solar and wind. Two approaches. We used pumped hydro storage at the end for most of what we do on electric vehicles for a variety of reasons. In general, we want to make sure that the vehicles can provide not only energy but also reserves. We want to make sure that we can control how many vehicles are connected at all times, and we want to make sure that this is as flexible as possible as an approach to be scaled up into, let's say, models where there is actual pumped hydro storage in the system. Another approach that has been suggested working with Energy Exemplar, and I think is more elegant. We still have some let's say, learnings to be done there, but using a battery class and a purchaser, we could, let's say, have a bit more elegant and separated approach of modeling electric vehicles as a separate energy grid, where the purchaser is actually the one discharging the vehicles when the cars are driving. So we did this initially in 7.4. We will update it to 8.0 soon, and so there's a few things that we want to look at, just to give a couple of justification of why we didn't do it, let's say, in a more elegant fashion. At that time, we couldn't really capture the fact that AVs were not always available, and that's why pumped hydro was more flexible in that. And we couldn't capture the degradation of the battery, which we think is very important when we try to talk about arbitrage. There is a concern from car manufacturers, but also at the system level, there is a different balance between energy and services that we see coming from electric vehicles. And if we don't take into account that a car has not been designed to do 20 cycles a day at full power, then there will be issues. We are very optimistic about what the batteries of an electric vehicle designed for mobility can do. If we connect it to a supercharger to do V2G and multiple cycles per day, they will not last your estimated 10 years. So we think degradation is a very important element to be taken into account, and we try to do that. So how did we do that? We just put a very simple approach. We are going to upgrade that with other algorithms. We had some discussion also with the support team. And so next year we will start a new round in 8.0 where we will try to improve this a little bit. But for the time being, we do have a number of cycle constraint. And the key point of this slide is that what happens as soon as you put a constraint on degradation, so that there is a cost associated with discharging your battery because it reduces the life. What you see here is that essentially once you include degradation, the number of cycles that are done for arbitrage significantly drops. So the potential for arbitrage using electric vehicle is very often overestimated without taking into account the degradation of the battery. What happens on the other hand is that there is more headroom and footroom available to provide reserves, which we think is, especially for wind, the main value proposition for electric vehicles, especially if they are connected at night and they are available for providing reserves. That can help a lot reducing the balancing cost in the system. When it comes to solar, though, you do need to do some cycling, but probably a cycle per day would be enough in most cases. An extra element there is that there is an impact on pricing. So once you include degradation, there is a less significant impact on reducing pricing, which from a regulatory perspective has to be taken into account as well. Couple of words about the Barbados case, just to put it a bit into context of the, let's say, the first case studies that we did. We're looking at a fairly aggressive scenario here with a 20%, let's say, conservative share of EVs in 2030. I don't think we're on track with this as well. There's been some start and stop. And a very ambitious target of getting 50% on the road, which means at one point in the next decade we need to be 100% on new vehicles being electric vehicles. And we studied especially the impacts of the more aggressive scenario, because even if this is not going to be 2030, it might be 2040 or 2050, and this is where you really see the impact of electric vehicles becoming very significant. One interesting element that goes beyond the modeling aspects that is often overlooked is that, yes, you need more electricity. You will probably increase the cost of electricity for a whole system because you increase the short-term marginal cost in many hours. But look at what happens on gasoline demand. So this is, in energy terms, these are gigawatt hours of fuel and gigawatt hours of electricity. The efficiency improvements of an electric vehicle will offset significant fossil fuel imports in end-use sectors. And it goes back to the previous discussion about decarbonizing the energy sector and not just electricity. On the other hand, sitting down with the finance ministry, they say, well, but this gasoline here gives us significant fiscal revenues, and what do we do about it? So maybe we can talk about general equilibrium models there, but this is beyond the scope of my presentation, but this is something also to be taken into account. So there's a lot of unintended consequences to be taken into account when you do this kind of exercises in policy. Another interesting element here is that to charge synchronized with solar, you really need to do something on public charging infrastructure. That is not obvious in many, let's say, emerging economies. The public charging infrastructure might not be there for some time, and without that, it's very difficult to expect to have vehicles sitting at work being charged when the solar generation is there, which might be a challenge as well for the implementation of what we see in the models. This is very difficult to read. Sorry about that. So going from left to right, essentially in both charts, what you see is from less beneficial charging strategy to more beneficial charging strategy. And it goes from uncontrolled evening charge, which is essentially going on top of the peak, all the way down to vehicle to grid during the day, providing also ancillary services, which seems to be the best one. There is a step here, so essentially the non-supplied energy, so the adequacy challenge, as soon as you start charging with a little bit more controls, so either charging at night with some controls and with vehicle to grid, or during the day, adequacy doesn't seem to be an issue, so there is no increase in the non-served energy. It's marginal. And what happens on renewables curtailment? This goes down when you charge during the day, because with very large shares of solar PV, wind integration is supported as far as ancillary services are concerned, but not really on the energy side of things. If you want to integrate more solar PV and reduce curtailment, which without doing day charging in this scenario is about 10-12%. It's a small island, so that has to be taken into account, becomes significant. So essentially, reserves for wind and some energy arbitrage for solar are key in this kind of high solar and wind systems. And the last slide on this study, so we published a paper to try to get some of the methodologies we used peer-reviewed. So there's a paper from last year where we looked at a few additional elements to what could be, let's say, easily translated into policy. One of the, let's say, petty projects I had for some time was to see how this helps in a system where you do need some battery storage for operating the power system with solar and wind, to reduce the amount of investment you need on the grid side on batteries by smartly charging your electric vehicles. And so we did something similar to what you do with estimating the capacity value of solar and wind, so effective load carrying capability analysis, so we try to do that reversing it and just try to see how can we keep the reliability at the same level by reducing centralized battery storage capacity by changing the way we charge the vehicles. So essentially here we have no electric vehicles and we have 150 megawatt hour and we meet the reliability targets of the utility. Actually we exceed them. This is about an hour of storage, so it's not a very large battery. It's really to allow to black start thermal generation even with uncertainty. The model includes uncertainty, so there is a stochastic unit commitment and different wind profiles in the day ahead. And to make sure that we reduce the amount of battery, we look at what is the best way of charging the vehicles that would allow you to save some money on investing on the grid. And so unsurprisingly in this case, again, the best scenario is always vehicle to grid, charging during the day and providing reserves, which allows you to save 30 megawatt hour out of 150 megawatt hour in terms of the battery capacity. And so essentially this could be money that could be used to roll out the charging infrastructure and to maybe top up a little bit the loss of income from let's say, the reduction in taxation from gasoline sales. So there's a few insights for policy as well. It gets a little bit complex to try to explain it, but we thought it was important to try to assess what is the impact on reliability of different charging strategies. And we don't see here, for instance, what is the impact on reliability of putting all the vehicles on top of the evening peak. Well, what is the impact is that it goes up. You actually need, in addition to the electric vehicle, additional battery storage to keep the same reliability level if you do uncontrolled evening charging. And then finally, what we're doing now based on these scenarios is to develop a bit more on nuances on 100% renewable electricity, because now it's becoming the key policy for the government. So we have a question mark around biomass. So can we roll out what we had already in the 2016 study, which is a tripling of the biomass capacity, where you have dispatchable biomass as the only dispatchable capacity in the system in 100% renewable, the rest being solar and wind. So the biomass scenario here is essentially about a third, quarter of the electricity from biomass, and the rest being solar, wind, and of course significant battery storage. What if we don't really have much of biomass? We try to push for a decommissioning of everything we have in the system, put flexible biomass capacity for 80 megawatt and the rest solar and wind. Well, it seems still to work, both in terms of reliability and in terms of energy balance. We rerun the LT also to see what would be the optimal mix. A word on this is, let's say, let's not try this in bigger systems. This is an LT with 24 slices per day fitted chronology for 20 years. So again, try to do that for Europe. You might need to wait a bit for the results. So for a 150 megawatt power system, this solves in a couple of days. So this is not really applicable to, let's say, the European model you saw before. But in this specific case, we're fortunate enough to have a small system to try this. And the results are quite interesting. So we need a really significant increase in solar if you take out the biomass or reduce the biomass significantly. Wind pretty much stays the same, and wind is still a question mark. Storage capacity increases quite a bit, but not as much as we thought, so it's actually doable. The question is, where do we put 300 megawatt of solar in such a small place? So finally, what we see is that 100% renewable electricity, let alone energy, is really a topic for further work. There's a lot of interesting work coming out of UCC, for instance. There is more work from different angles where it's becoming a question of disagreeing on the how, not on the if. So I think it's very important stream of work where tools such as PLEXOS can help in giving the confidence that such scenarios could be, let's say, doable in the medium term, and looking at how this could be operated is the very next step that we need to really discuss to build a consensus on the topic rather than having a discussion about at how many minutes time step you're running your model. So with this one, I'll conclude in my presentation with a couple of ideas for further future work. So we'll definitely apply this approach to additional countries, both at global level, so large-scale models like in the case of Europe, but also more of this 100% renewable roadmaps for islands, where the focus now is shifting from electricity only to end-use sectors. how to best use the new features of PLEXOS 8.0 to do more sophisticated EV analysis. There is something to be done, I think, on the stochastics that could be interesting using the new multi-stage stochastic hydro. So reliability, assuming the vehicles will be available at a certain time of the day in a deterministic fashion is a bit risky. Doing stochastics on when the vehicle might actually be connected in different days of the year, I think is another very interesting way to look at reliability. So not just on the generation profiles, but also on the availability of these vehicles as batteries on wheels. And then, of course, trying to roll out the different approaches to advise policy on how to go about electric vehicles deployment in a way that is system beneficial, I think is another very important area of work. With this, happy to take any question. Thank you.